Okay, take it away. Thank you for being with us in the middle of the night there.
Okay, thank you. Okay. So I would like to start by thanking Professor David Snoke for the opportunity to present my work. So the title of the talk is Quantum Reservoir Networks, and I wrote that it is for analog signal processing, but it is not really limited to analog signal processing. But what I will present is mostly about analog signal processing. So my name is Sanjib Ghosh, and I'm working with Professor Timothy Liu, and I'm actually talking on behalf of him. And I am from Nanyang Technological University, which is in Singapore. Okay, so here is my plan for the talk. So in the beginning, I will introduce some concepts of neural networks and the classification of neural networks. And then I will introduce the concept of classical reservoir computing and how Exciton-polaritons can be used for this reservoir computing implementation. And then I will show some self-correcting feature, and this is about digital computation rather, but it will be very short. And then I will go into the main topic of this talk, which is quantum reservoir computing and how it can be used for different quantum, so-called the quantum task, which is quantum classification task, quantitative estimation, universal state recognition, and then some robust state preparation tasks. So here
your screen share doesn't seem to be working. I'm just getting a black screen.
Oh.
So there we go. Now it's working.
Okay. Okay, so the classification of neural network based on the type of task that it does. For example, whether it is doing classical information processing or quantum information processing, and the computing system it is using, whether it is a classical hardware or quantum hardware. So we can classify neural networks into 4 categories. And this one is the purely classical category, which is classical task with a classical system. And these two are the hybrid type, which is either the system, the physical system, which is quantum, or the task, which can be quantum. And actually in the recent time, what we see the many works, which is about quantum machine learning, they are falling into these 2 categories. And they're very interesting because it is shown that if we use some quantum hardware, large scale quantum hardware, which is actually not available in full scale, but still if it is available, when it is available, this can enhance the learning capacity of a neural network or speed up solving some classical tasks. Also, the classical neural network can be used for solving quantum problems, such as difficult quantum many-body problem can be solved with classical neural networks. And then the quantum experiments can be controlled by classical neural networks. And then this 4th one, which is like I would call fully quantum, which is doing some quantum task with a quantum computer or at least quantum hardware. And there have been also some proposals, but all these proposals are assuming that the quantum computer is fully available in its full scale. And we know that it is not available yet. So here our work falls under this category, but we are not assuming that the quantum computer is available. We are rather proposing a hardware independent of the quantum computer. So let me begin with, again, give some introduction about the neural network. So one of the motivation for going into the neural network based computing system is the so-called von Neumann bottleneck in the present day computer, where the computing processor and the information stored, the memory of the computer are located into physical space. And when the computation happens, the most of the time spent is by communicating between these two physical space or the physical place. And this is why it is thought that if we use a neural network architecture where we do not have to spend so much time in this communication, and then we can save some computation time. But in my point of view, it is more like it can be a add-on feature in the present day computer where we can get some benefit by just adding a small say hardware which is based on neural network, like something like a GPU. So there are major two types of neural networks. One is the feed-forward neural network, where so suppose that we consider this neural network where these dots are representing the neuron nodes, and these lines are representing the connections between them. And in the feed-forward neural network, the information goes only in the forward directions and it never comes back. And this is probably the most frequently used artificial neural network. And it is used for various tasks. I mean, this is like a large class of tasks that can be done with this one. And the second type is the recurrent neural network, where the information can go back and forth and make loops and so on. So it has like a sense of dynamics inside. And because of this dynamical property, this is good for time-dependent problem. And also good for predicting complex time series problem, a speech recognition problem. And it is actually used by many technological companies. And however, there is some problem with this one, and that the training can be difficult because it is a dynamical system, and it is also nonlinear because these nodes are nonlinear. And thus this is a nonlinear dynamical system, and there can be bifurcation. And because of that bifurcation, the training procedure can be non-converging, and even when it converges, it can be very slow. So here comes the idea of reservoir computing. So this has emerged, the same idea emerged in two different communities, echo state network in the machine learning community and the liquid state machine in the computational neuroscience community. And now they are somehow generalized to the under this name, the reservoir computing, which is coming from this observation that if the network is really large, then actually we can keep the most of the network connections as untrained or not optimized, and we can only choose few connections to optimize. And this is enough to do many tasks. So how it happens is basically the idea is that we take a large network which is randomly connected, and thus we do not need any optimization here. And then the input signal goes into this large network, and then and then dynamic happens. So it has to be a dynamical system. And then we take the readout from these nodes as the output of this network. And then we apply a single layer, a neural network, to get the final output. And we only train this single layer here. And because it is just a single layer and it's kind of a linear problem, and we can do it much faster than optimizing the whole system. And this has been because of this flexibility that we can choose the network connections random. It has a large success of implementation in many systems. For example, electronic system, optical system, spintronic system, solid state NMR, and many other systems that has been noted in this recent very nice review paper. The type of task it can do is typical task is time series forecasting. So meaning that by learning from the past of a time series, we have to predict the future. Similarly, some recognition tasks such as digit recognition or speech recognition. So here is the example of Exciton-polaritons reservoir. So this is now my reservoir that we were talking about. a network with random connections. So as from the previous talk, which was really nice introduction of this Exciton-polaritons system, and of course much more. But with that introduction, we can now understand that polaritons forms condensate, and each of these nodes are actually representing a condensate with nonlinearity. And the connections are linear connection between them, which can be formed also in the polariton system. And then it is a gain loss system where I can put some light into the system, and then dynamics will happen here. And then it's also lossy system, so it will emit light, and that will be that can be collected as the output for the network. And then the final output is given by this formula, which is this output measurement, which is basically the intensity from each node. And then we multiply with a matrix to get the final output. And this is a linear equation. So the training is basically to find out this matrix. And so the training is here again, it is a linear problem. So relatively easy for optimization, and usually linear regression is enough. But even this can be also can be done by hardware optimization, as we have seen in the previous talk. Very nice talk. And this has been theory, and then the experiments also is done, and that the polariton indeed can be used for this forming this reservoir, and then the input can be put into the system with light. And again, there is a SLM here, so which is basically controlled by a computer as well, and then the CCD here to take the output measurement. So of course it is not purely optical, there is some involvement of the classical, digital computer, but I would say this is like a enhancer of this task. So we can see it here. So if we use just purely a linear classifier, then the success rate of recognizing these handwritten digits are following this graph, this line. Whereas with this sample, because of its nonlinear property, we can enhance the success rate a little bit. So this is like an enhancement on top of the like classical the computer. And there are other systems also. We note, it is noted here that we can compare with other hardware system. Compared to that, it has a higher rate of success. So now another example that we can form, we can take a small scale polariton network to form a universal gate like a Toffoli gate for digital computation here. But the underlying system is still analog, because the reservoir computer is an analog computer. And what we do is that we use this to model a universal gate. And this can be done with a very small reservoir. Now, what is the advantage? The advantage is here. So in regular computer, the circuit, the electronic circuit, it might not be perfect. So there can be some error. And then this is why we need error correction code. What it does is that if there is some error in the input, then if there is again error in the circuit, then the output error will be larger than the input error. And thus the error will propagate and become larger and larger along the line. So we need some error correction code to decrease this error so that it is controllable. And this is the error correction, and this needs time, extra time. So what we saw here is that with such this reservoir computer computing framework, if we form the universal gate, then the gate itself is self-correcting. So meaning that if we put some input error, signal with error, the output error becomes smaller than the input error. So then again, if there is some error here still, then it will go into the input of the next one, and the output will be even smaller and smaller. So we do not need an extra error correcting code here, at least in theory. So it has not been proved in experiment yet. So now let me go into the quantum reservoir computing. in the quantum reservoir, we also call it processing. So the idea is quite same. So only the change is that instead of, so previously we were putting some classical information, now we put quantum information. And this can be, I mean, we can imagine it as a pair of photons, and that can be entangled. And this entanglement can be the information, quantum information. The reservoir is basically the same idea, but then again, the nodes now become a quantum node. So meaning that it has to work in the few photon regime. So this is not condensate. And so in theory, we consider it is a two-level system. So either 0 photon or 1 photon, but it can be few photons, like 0 photon, 1 photon, 2 photon, and then it has to stop there at some point. And those nodes are then connected. So in other words, these are very highly nonlinear cavities. And then they are connected with random linear coupling. And then it will form a quantum reservoir now. And these input information in terms of photons, they fall onto this reservoir and get absorbed. And then some dynamics happens again. And then after some time, because it's a lossy system, so it will emit light, and we will just detect those photons to measure the average number of photon occupation in each of the node. And then again, the final output is given by this linear formula, that this output measurement, which is basically the mean intensity, is multiplied with a matrix. What can we do with this? So for example, we devise a problem like in classical classification tasks, such as like recognizing which picture is cat and which picture is dog. Then we here consider a quantum analog of that, which is we have to now recognize which is entangled and which state is not entangled or the separable. So we take a random collection of quantum states, 50% of which are entangled and 50% of which are not entangled. And then the task of this network is to find out which one is entangled and which one is not. And the prediction of this network is this color code, which is the entangled are this magenta color, and the separables are this bluish color. And the circle is a theoretical boundary. So if inside this circle, that means it's theoretically entangled, and we can see the prediction from the network is largely inside this circle. And here is the more success, I mean, accurately the success rate, which is like whether it is successfully recognized, whether it is separable or entangled. And we have considered different type of quantum states, like ranging from squeezed thermal state, photon added state, photon substructed state, and then the Bell state, bound entangled state. And we see that there are high level of success. However, it is note that it is not 100% accurate. And this is the signature of a neural network or a analogous system. So it's never absolutely correct. So we can only reach more and more accurate situation by increasing the size of the network. But it is, again, not absolutely correct. Then another example of task that we can do is a quantitative estimation. So the previous one was a qualitative estimation, which is whether it is entangled or not. So it's a 0-1 kind of output. Here, the output we can assign as a quantity. And the quantities are like such as negativity or entropy or the purity of the state. And these are very important state, and theoretically we often look at these properties to characterize the quantum state. And however, experimentally to estimate these quantities are rather difficult, because these quantities are very nonlinear property of the input quantum state. And note that the quantum measurements, which is the POVM measurement, are linear in the input state. So to get these nonlinear quantities, what we have to do conventionally is that we have to estimate what is the rho in, or density matrix of the quantum state. And then we can, if we know the quantum density matrix, then we can calculate whatever quantity we want theoretically. However, we cannot estimate it directly in the experiment. And this platform can do that. So for example, we assign negativity, which is like a quantity, which is a measure of how strongly the state is entangled. So if it is very large, that means it's strongly entangled. And if it is low, that means it's not. And here the predicted value versus the true value we plot. And this black line is the perfect line, which is like when they are equal. And we can see there are points which are not very close to the black line, and there are points with different color which are very close to the line. And these are representing different reservoir size, the network size. So if the network size is very small, the prediction is not very good. But if the network size is very large, means these are with 2 network nodes, and these are with 4 network nodes. So then it becomes accurate. And then similarly for other quantities, which are very nonlinear property. So we find that this QRP, which we call this QRP network, can directly estimate nonlinear properties, and it simplifies the experiments requiring multiple measurements. Then another task, which is quantum tomography. This is again a very important task where we have to estimate what is the density matrix of the input quantum state. And in the conventional quantum tomography, we need to measure a large number of correlations, because in the density matrix, we have many correlations, and the number actually grows exponentially with the number of qubits. And thus it is considered a very hard problem. And the correlation measurement is again not very easy. So measuring a intensity is rather easy, but measuring their correlation is difficult compared to that. So here we say that we can do that, at least we can try. And here we do not need to measure any correlation. So here all these are intensities from each node. And then we find that indeed we can do tomography. And not only that, we can do tomography of both the type, which is continuous variable or discrete variable. So discrete variables means qubits, q-trit, 2 qubit, and so on. And the continuous variable examples are Gaussian state, squeeze state, etc. And this can be done in the same platform. Now, the question is, how many nodes do we need in the reservoir? And it turns out that it actually also grows exponentially with the number of qubits. So this is not very helpful. Then this will just explode the reservoir size. But then we find this concept of time multiplexing, which is basically, if we can resolve the dynamics of each of the node, then we can take the measurement at different times. And in this way, we can increase the number of output. And then we can reduce the number of reservoir nodes in the reservoir. So here are some examples. So if we do not use this time multiplexing, then we need, for a qubit, we need three nodes. For q-trit, we need 8. And for 2 qubit, we need 15. So which is beyond this graph, the scale. However, if we use the multiplexing, then these 2 qubit, we did not reach the perfect fidelity, which is 100% accuracy. But if we use the multiplexity, then by using only, say, 2 nodes, reservoir size, 2 or 3 here, we can get the perfect accuracy. So we kind of, if the dynamics can be resolved, then this problem of exponential growth can be handled. So then another very important question is that the density matrix has to be physical, meaning it has to obey some rules. For example, it has to be positive because the eigenvalues of this density matrix represent probability, and the probability has to be always positive. But the reconstructed density matrix, it might not be perfect one, so then it might not represent a physical system. So conventionally, we need maximum likelihood estimation, meaning that we have to find out the closest physical density matrix with respect to the estimated one. And this is a complex, again, problem. What we see here is that if there is no measurement error, of course, there will be some measurement error, but for theory, let us consider that there is no measurement error. Then we find that the density matrix is always physical. So there is no problem. But then we go into this case when there is a large measurement error. So here there are some measurement error because maybe there are not a sufficient number of statistics. And then the density matrix we find that the density matrix is also physical if the number of training sample is sufficient. Meaning that we have to train the system, and we use the so-called supervised learning, where we need to some example state where this density matrix is known. And how many samples needed, that is the question. And then we find that we need a rather large number of, if the large number of sample is available, then the output estimation is always physical. And here we see that if the training sample is rather low, like 8 training sample, then we find that the minimum eigenvalue of this estimated density matrix is sometimes negative, and which is not okay. And then we go to a larger number of training sample, then we find only, I mean, with the same state, we consider the same state, same set of states, and then we find only one wrong density matrix. And then we go with the 64 training samples, even higher, then we find there is no wrong estimated density matrix. So then another task that we can do with this one, which is the quantum state preparation. So here the problem is actually exactly the opposite one. So in all previous examples, the input was a quantum state and the output was a measurement, which is a classical number. Here we do the opposite, which is the input is a classical laser, which is falling onto the quantum reservoir, and it is absorbed by these quantum nodes, and then they will emit light, and those emissions will be quantum in nature because these nodes are quantum. And we take those as the element for preparing a final quantum output state. And we get the final output state by linearly combining all this emission. And this linear combination can be done with linear optical elements. And mathematically it represents by this formula, which is the output annihilation operator is a linear combination of all the annihilation operator corresponding to these nodes. And these coefficients are the linear optical elements. And we assume that these linear optical elements is tunable. And if that is possible, then we can prepare a range of quantum states that can be considered quantum resource for various quantum processing problems. So for example, Schrodinger-Cat state, single photon states, entangled states, noon states, cluster states, and discordant states. And these are all in the practical condition, meaning that we have large loss and also noise, etc. So let me then summarize what I have shown to you is that reservoir networks are a robust platform for analog information processing in the classical regime I'm talking about. And it is also self-correcting and can be universal. And the main network needs no optimization. And thus it is relatively easy to engineer because we do not need to control very accurately between the connection between the nodes. And this is very important for a quantum processor. In the present day quantum computer, the main challenge is really the engineering challenge, because we need a very accurate qubits, and then we have to control the coupling between the qubits very accurately to implement a quantum gate. And this is really challenging, and the engineers knows how challenging it is. And however, what we propose it cannot be compared with a universal quantum computer, but it is rather it can do some specific tasks. However, the engineering challenge is much less here. So we already consider a lot of noise, decoherence, etc., and fully random system parameters, and it works perfectly well. And it can do the tasks such as we have seen: quantum recognition task, quantitative estimation, quantum resource preparation, and quantum state tomography. And finally, I would like to acknowledge the contribution from the people who have worked in this: Timothy Liu, our group leader, Thomas Patarek, Mikhail Matuszewski, Daniel Isanvito, Tanjung, Kisnanda, Hua Wenzu, and Andre Zopala. With this, I would like to end my talk.
Okay, well, thank you very much. And let's see, if you end your screen share, then that'll allow other people to be visible. So again, for those of you who may have joined recently, the way we're going to do questions is if you send me a private chat, then I will either read it for you or unmute you. So just off the bat for myself, the speed up here in doing these neural networks, is it fair to say that it's partly just because you're doing massively parallel computation with these systems? That, I mean, in principle, if you had a digital computer with 1,000 parallel processors, it would be like a 1,000 node optical system with polaritons. I mean, is the payoff here because with these classical optical systems, you can do massively parallel things?
Yeah, I agree with you perfectly. I think it's very fair to say. It's basically the reservoir network is, I think structurally it is basically a parallel computation thing. As you can see, we have many nodes and they're kind of interacting with each other, but finally the output is just measurement output from each of the nodes. And actually we can also show that if there is no connection between the network nodes, which is basically considering many disconnected independent nodes, it still works.
Mm-hmm, mm-hmm.
And thus it proves your
so it's not exponential speed up, but it's basically massively parallel linear speed up if you can make a big thing with a lot of nodes.
Yes.
Yeah. Okay, are there other questions? I'm looking to see on the chat list here if anybody wants to jump in there. At the moment, I do not have any more questions in the queue. Okay, so while I'm going to give people a couple more seconds to ask questions. So the plan is, let me go ahead and screen share the schedule again. Let's see here. Okay. So we're going to break. We will start strictly at 1 o'clock with the next talk. So we have a meal break at the moment. We'll start right on time at 1 o'clock with this Victor Galitsky's talk. And then I also want to point out a schedule change from some of the schedules I sent out last week. That at 2 o'clock we have Scott Aronson, who is going to start us in on a discussion talking about sort of general principles of computing. And then we'll go in sort of right from that into a panel discussion. And I believe at this point there are no changes in the panel, that Paulos Lavadakis will be able to be with us for that panel, even though he wasn't able to be with us this morning. So if I don't get another question in the next 10 seconds, we'll go ahead and take a break. And I'll stop recording at this point. Let me say I'm going to stop sharing. All right, then I'm going to stop recording.